Welcome to this explainer. Today, we're taking a massive leap in how we view the physical world around us. Up until now, you've probably just looked at objects moving in simple straight lines, right? Forward, backward, left, right. In a straight line, it's pretty easy. You just slap a plus or minus sign on it to figure out where things are going. But let's be real. To understand our actual world, straight line math just isn't going to cut it. The real world operates in 2 dimensions, even 3 dimensions all at once. So today, we're giving our toolkit a major upgrade.
And to see exactly why we need this upgrade, I want you to think about this for just a second. Why does a thrown ball follow a curved path instead of a straight line? Think about it. If you toss a baseball to a friend, it doesn't just travel in some rigid, laser-straight diagonal line. No way. It arches. It curves beautifully through the air. Answering that exact everyday question is our main goal today. And by the time we wrap up, you'll see how breaking down that curved path proves that physics is basically the ultimate cheat code for understanding reality. Okay, so here's our game plan for today. First, we'll break down scalars versus vectors. Second, we're going to look at the head-to-tail rule. Third, we get to the fun stuff, throwing balls or projectile motion. And finally, we'll wrap up with uniform circular motion.
All right, let's dive right in. Section 1, scalars versus vectors. So, in physics, we basically split physical quantities into 2 different camps. Over on the left, we've got scalars. A scalar is literally just a magnitude, meaning it's a single number and a unit. That's it. Think of the mass of a textbook or the temperature outside. If a solid block of aluminum has a mass of 2.7 kilograms, well, actually, that's the whole story right there. We don't need a direction. But on the right side, we have vectors. And vectors, they are a whole different beast. They demand both a magnitude and a direction to make any sense at all. Take velocity, for instance. If you're zooming along at 50 miles per hour, to really know where you're going to end up, you absolutely have to know what direction you're going. Displacement, velocity, acceleration, these are all vectors. They literally demand a direction. Which brings us perfectly to Section 2, the head-to-tail rule. Because now that we have these vectors, we need to know how to actually add them together. Now, what's really interesting here is how the physical lengths and directions of these arrows actually represent the vectors themselves. If we have vector A pointing one way and vector B pointing a totally different way, we can literally just draw them out on a page. The math turns into this visual geometry puzzle, which is great because it makes it wonderfully easy to just see what is happening in the real world. And here is exactly how you solve that puzzle, step by step, using this graphical method. First, you take your vectors, A and B. You physically take the tail of vector B and place it right at the head, the pointy arrow part, of vector A. You just slide it right on over. Second, you draw a brand new line starting from the very first tail of A straight to the final head of B. That new line, that's what we call the resultant, or R. Notice how it forms a triangle. That's exactly why this is also called the triangle method of vector addition. It is the literal physical sum of the 2 vectors.
Okay, moving on to Section 3, throwing balls, better known as projectile motion. This is where we apply our new tools to real objects flying through the air. This brilliantly illustrates exactly what happens when you throw something. Look at that beautiful curved parabolic path. This is the trajectory that literally any thrown object takes, whether you're tossing a baseball, a football, or a water balloon. Once it leaves your hand and is in flight, it becomes a projectile. But why does it make this specific curved shape instead of just a straight diagonal line? Well, to really grasp this, we have to look at the motion as 2 completely separate vectors happening at the exact same time. This was actually Galileo's grand discovery way back in 1632. He realized that you kind of have to split your brain in half here. The horizontal forward motion, that has a constant speed with 0 acceleration. Once it leaves your hand, assuming we ignore air resistance, nothing is pushing it forward or holding it back horizontally. It just goes. But the vertical motion, that operates completely independently. It has a changing speed because there is a constant downward acceleration acting on it. And that acceleration, as you probably guessed, is the force of gravity.
So this crucial point is captured perfectly in this quote from the text. It says, one component is along a horizontal direction without any acceleration, and the other along the vertical direction with constant acceleration due to gravity. Gravity only pulls down. It completely ignores and leaves alone that horizontal forward motion. And by adding those 2 completely separate vector components together at every single second, using the exact same logic as our head-to-tail rule, we get that beautifully, mathematically perfect curved parabola.
Now let's transition from flying objects to spinning objects. Section 4, uniform circular motion.
Take a really close look at the vectors in this circular diagram. When an object follows a circular path at a constant, uniform speed, something that feels a bit like a trick question happens. You might look at this and think, hey, the speed is constant, so there's no acceleration, right? Actually, no. Wrong. Remember, velocity is a vector. And what does that mean? It requires both magnitude and direction. So even if the speed stays exactly the same, the direction is constantly changing every single fraction of a second as it curves around that circle. And because the velocity's direction is changing, the object is technically constantly accelerating. Crazy, right?
But wait, if it's accelerating, which way is that acceleration vector pointing? The answer is always inwards. That acceleration arrow is forever pointing toward the middle of the circle. We call this centripetal acceleration. The word centripetal actually comes from a Greek term meaning center-seeking. The acceleration is quite literally seeking the center of the circle, constantly tugging the object's direction inward so it doesn't just go flying off in a straight line.
Our source text gives us this great, slightly quirky example to really cement this idea. Imagine an insect trapped in a circular groove with a radius of 12 centimeters. It steadily completes 7 revolutions every 100 seconds. Now, because it's moving steadily, it has a constant speed. But because our little bug is going in a circle, its direction constantly shifts. Therefore, its acceleration vector is never constant. The magnitude, like the actual physical amount of acceleration, stays the exact same, but the vector itself is always pointing in a brand new direction as the bug runs around that groove. It's just a perfect real-world illustration of why direction matters every bit as much as the amount.
Which brings us to one final, slightly provocative thought experiment. If gravity suddenly just turned off while a baseball was mid-air in its parabolic arc, what path would it take next? Think back to Galileo's concept of independent vector components. Without the downward acceleration vector of gravity constantly pulling on it, what vector is left to dictate the ball's motion? I'm going to leave you to ponder that 2D physics puzzle. Thank you so much for exploring the physics of our reality with me in this explainer.